Hello, everyone. Welcome to our final presentation. And our team's project is Medical Imaging RPA System. And we're a team of 4, and my name is Feng. Other team members are Fangyuan Huang, Yiwu Chen, and Zhenjie Zhou. In the last presentation, we introduced an RPA workflow to classify imaging requisition forms. Also, we showcased everyone's contribution, including online facts, cost analysis, form classification, serverless, metrics, and error handling. And in today's presentation, we'll discuss the result of 3 different approaches, including the RPA solution we introduced last time and 2 other improved solutions. And then we'll discuss the limitation of our solution and some possible future directions. And lastly, we'll provide an overall project completion. And for the RPA solution, we first get all the text in a PDF using Aquaforest, which is a third-party OCR service. And then we have a definition of unique keywords. A unique keyword is a word that only appears in one type of form, like the word computed tomography shown in the right image, which is the full name of CT forms, and can only be found in CT forms. Thus, unique keywords can be used to identify the form type. And for each type of form, we check if the text contains its unique keywords. If it does, we'll save the PDF to the corresponding folder. And as a result, the accuracy of this solution is around 67%. And for the cost, it's about 10 cents for each page, which is much lower than the cost of manual work. And the advantage of this solution is scalability. We can easily add a new type of form. We just need to find its unique keywords. And talking about the disadvantage, there are some forms that don't have any unique keywords. Instead, the imaging requisition type is specified by the text in the exam requested field. For this kind of forms, this solution cannot classify them correctly, and they will be saved to others' folders and need further classification.
So in order to improve from the 67% accuracy given by the keyword matching, we first look into the cause of previous errors like Feng mentioned. It turns out that most of the errors are due to either there are no keywords presented or multiple keywords found. For example, on the left is one successful example, very similar to what Feng showed previously. You can find that there's a very simple unique keyword on the top that can help us identify. However, on the right, it is a failed example for the first approach. Here you can see we have multiple keywords presented on the top of the form, like X-ray, CT, and ultrasound. In such cases, the unique keyword approach will fail as the algorithm would not be able to reason which keyword is the correct one to use. However, we noticed that in most of those ambiguous cases, like the one on the right, they usually present a field called exam requested, like Feng mentioned, and then its value will usually contain one unique keyword that can help us to correctly identify. As a result, we come up with our second approach, that is, we add a key value pair evaluation if none of the keywords found or more than one unique keyword is found. In order to achieve that, we noticed that we can leverage the help of Azure Form Recognizer, which will help us to extract key value pairs from PDFs. And then the key here is the exam requested, and then its associated value will be the content where we can search the unique keywords from. However, there's one immediate challenge, which is migration. In order to use the Azure Form Recognizer, we have to use it from the Azure platform instead of the Power Automate pipeline we were having for our first approach. Luckily, Azure provides a Python SDK, which made this process very, very easy. As a result, we migrated from SharePoint with Power Automate to Azure Blob Storage with Azure RPA service. We were able to improve the accuracy from 67% to 80% in our test set. And then the overall cost was even reduced from 10 cents per request to 6 cents per request, mainly thanks to avoiding the cost of third-party OCR API call.
We still want to further improve the accuracy. To figure out why our classification went wrong, the team designed another pipeline to turn the PDF into JSON dictionary and mimic the pipeline conditions locally to investigate the cause of error. At the end of investigation, two main improvement methods were applied to further improve the file classification accuracy. First, the search keyword gets refined. For example, the keyword ultrasound was used to classify the ultrasound type of document, but some other types of file may also contain this keyword. So the team further improved this by using the unique keyword ultrasound consultation instead, because a more specific and longer unique keyword will have less undesired collision. Second, key value pairs get improved. The key exam requested is used to get the type of the request, but different form of this file may contain different form of the keyword. So we add more actual keys to the function to ensure the value can be acquired successfully. After the above processes, the accuracy improved from 80% in the second iteration to 97%.
The existing solutions requires heavy manual work, such as scanning, data transfer, and analysis. It takes about 5 minutes per request. And up to today, there's over 8,000 requests pending in the backlog. Our proposed solution aims to remove such tedious work and optimize the operational excellence. And this improvement can be measured in time consumption. Here is our proposed system architecture as shown in step 122. The duration of storing incoming fax requests to Azure Blob service takes an average 3 seconds per request. And the execution of each Azure function serverless invocation, including the text extraction using Azure Form Recognizer and saving forms to dedicated containers, takes an average of 15 seconds, which is step 3 to step 6 in the diagram. In comparison, we can see that the total time consumption is greatly reduced by 94%, from 5 minutes per request to 18 seconds per request. However, we do have some limitations. The first, our solution has third-party dependencies, such as Azure Services, Power Automate, and SRFax platform. Secondly, we use the pre-built document model. It is hard to tune the recognition result over 20 types of formats, and it results in high variance at non-standard formats. Lastly, we have the human-in-loop design currently, where those undecided forms require a second look. However, it can be further improved as a future work.
For the future work, we identify 2 areas of improvement. First, we can have a more robust form recognition system utilizing machine learning to further improve the recognition accuracy. For example, we can build Azure custom document model for each type of form. Second, we could deploy and evaluate performance at a larger scale to illustrate the operational excellence of our system.
So in summary, our work shows that RPA can be a great help to the current medical health system. First, it improves accuracy by reducing the chance of human error. Second, it reduces repetitive manual tasks, which leads to a better working experiment for hospital staff, which will in turn lead to a better patient experience. Third, it is very cost-effective. In our case, we found that the overall cost can be reduced by 98.4%, almost 99%. This is a great improvement. And most importantly, the RPA approach is fast and very easy to scale up. This is critically important given the current PHC has more than 8,000 requests waiting in the backlog, and then this number is only increasing over time. Each single request is a patient in need. By adopting the RPA technology, hospitals will be able to help more patients faster and save more lives. Thank you very much for your time, and then hope you enjoy our presentation.